Hi everyone, I'm Professor Bergasser, and in this video we're going to be doing a little physics trick, and that's figuring out whether we use sine or cosine when we're breaking down the components of a vector. Now we have lots of examples where we're going to have a vector that doesn't necessarily align with the coordinate system that we're choosing, and so we have to break down that vector into its individual components along those coordinate axes. And whether you use sine and cosine, it's very easy to get lackadaisical about just always choosing cosine if it's along the x-axis. But that's only for a very specific geometry. It may be that we have a different geometry or a different angle in which we've measured where we have to be careful about which one of these two functions we use, sine or cosine. So as an example to illustrate this, let's just take the example of me taking this ball here, tennis ball, and throwing it down toward the ground. And the angle which I throw it is measured with respect to the vertical axis. So I've sketched that in our coordinate system here, our xy rectangular coordinate system, and you can see that the vector is pointing off in this angle, and that angle is 35 degrees with respect to the y-axis, or in this case the pointing down axis. So there's a few ways that we can double check or either compute and figure out, double check which one of these functions we're going to use for the components. The first way is to use our mnemonic SOHCAHTOA, or probably more accurately our acronym, where we're looking at these trigonometric functions sine, cosine, and tangent. Sorry if that's a little unclear. And the O, A, and H correspond to the opposite, adjacent, and hypotenuse sides. So in this case, what we're doing is drawing a triangle where the vector is the hypotenuse of our triangle. So if we connect that with our y-axis, and this is a right triangle, then we can see that the adjacent side is here on the y-axis, the opposite side is parallel to the x-axis, and the hypotenuse is again lined up with the vector. So if we want to write down the components of this vector, so Vx and Vy, they're both going to be proportional to the length of the vector v, which is 5.2 meters per second in this case, and then the y component is aligned with the adjacent axis, and the adjacent corresponds to the cosine. So we can immediately write down cosine of theta for y and sine of theta for the x component. And we can even compute these numbers out. This is 5.2 meters per second times the sine of 35 degrees. And this works out to be 3.0 meters per second to our correct number of significant digits. And we can do the same for our y component, that is the cosine of 35 degrees, and that works out to be 4.3 meters per second. Okay, so that's one way of doing it. The other way we can do this is to look at or check on angle limits. Okay, so that's cases where the angle goes to 0 degrees or it goes to 90 degrees. So let's take the first case. If this angle 35 degrees goes to 0, then in that case the v vector is pointing entirely along the y-axis. And so if theta is equal to 0 degrees, then Vy is just equal to v. Now, the only way that can happen is if the trigonometric function I use evaluate at 0 degrees is equal to 1. And you should know by now that, of course, cosine of 0 is equal to 1, sine of 0 is equal to 0. So this has to be a cosine theta. All right? And we can do the same thing for the extreme case of 90 degrees. That's lifting this vector up so that this is a right angle. In that case, the v vector is going to point entirely along the x-axis. And so we would have Vx is equal to v. And sine of 90 degrees is equal to 1. So this has to be a sine theta. All right? And of course now we can double check to make sure that we got the same things. I reversed the order, but we do have the y component as cosine and the x component as sine. So that's a check. Now another way that we can check is the relative magnitudes of our components. Okay, so the angle I've drawn here is 35 degrees. At 45 degrees, we would expect this to split exactly between x and y, so the components should be equal. But if it's less than that, it should have a larger y value than an x value. And indeed, when we look at the numbers we calculated, we get 4.3 meters per second for y, 3 meters per second for x, and so that's consistent with our choice. So that's another check. So we've got 3 independent ways of making sure that we get our trigonometric functions correct when we break down the components. I encourage you to practice all 3 of these. They'll be very useful when you're breaking down vectors that are more complicated, or when you're in a test and you have to do this very quickly. It's nice to have easy ways to check that your answers are in the right direction.